really what we think it is. Thank you very much.
Thank you very much, Carlo, and I pass the baton to Freddy.
Thank you, Carlo. Thank you, Joachim. For me, it's a privilege and great personal pleasure to invite Steve to tell us how it all began with the presentation of ISR. You know that Steve had a very long career at CERN. He's very well known, especially for his central role in LEP, Lepton Collider, and the startup run one of LHC. However, I remember well his sharing of experience on the operation of ISR during long period. In particular, I remember how to keep beams for a very long time when the beam dump system is not fully operational. Steve, you have the floor for 20 minutes.
Thank you very much, Freddie, for the nice introduction. Doesn't seem like 50 years ago, but I guess it is because everybody's talking about it. I had a phone call this morning from one of my friends who worked with me in the ISR, and he knew about the program. And he said, very interesting, because the person who's speaking about the oldest accelerator, collider, is the youngest speaker. That's the first time I've been called the youngest for a long, long time. So I'm not trying to outdo Carlo, but these are the topics I'm going to talk about, so I have to be quick. I won't even tell you what they are, but you'll see. So the ISR, I think it's the almost forgotten first ever Hadron Collider. An amazing collider. It accumulated currents, 57 amperes, not milliamps or microamps, but amperes, with enormous dimensions. The cross-section of the beam was 3.2 inches, so it was huge. Unbunched beams with 3% momentum spread and an aperture of 4% delta P over P. One of the huge disadvantages was diagnostics, because you'll see later why. I think the ISR had a huge impact on accelerator physics, but sadly, and you'll hear this later from Ugo, I guess, not as much effect on particle physics. And a brief history, and it's been mentioned before, so I'll go quickly. Carlo's already done this. 56 studies started. 61, there was a study of the 300 GeV, which later became the SPS. But it was decided then, 61, to construct the ISR first. It was approved in 65, and in December 65, the budget was approved, 332 million Swiss francs, and started operation as foreseen in mid-1971. First beam in 1971 in operation for physics from 71 to 83. And these are three of the four people responsible for the construction. On the left was my boss for a long time, Wolfgang Schnell, excuse me, Renzo Rezzagotti in the middle, and Kai Silverskun on the right. And the missing person here is Kjell Jonsson, who was the leader of the project. It's IP5, you've already seen this, so I'll not bother. This is 0.1 and 0.8. These are the basic parameters. Important for various types of collisions with different species of particles. Quite a large momentum range. And very importantly, which I'll come to later on, it was a very small RF, 16 kilovolts maximum RF voltage, which nowadays is practically nothing. This was a control room in the early 70s, and the only thing which anybody will recognize there compared with modern control rooms is the analog clock on the back wall. Everything else is completely different now. It was a storage ring, and what it did was you took 20 bunches from the PS, accelerated them from injection orbit to storage orbit, and let them go. Let them go mean you switch off the RF, and this meant that the stored beam was a coasting beam or debunched. Hence, none of the normal electromagnetic beam diagnostics could work. This was a huge disadvantage for tuning the machine when it was in physics. The only two devices which we could see the beam with was a sodium gas curtain and a beam current transformer, obviously in each ring. And stacking, it's not difficult to understand stacking. If you look at this little diagram, it's a bunch beam coming in, being let go, and debunching. So that's how you build up a stack. You did this 200 times. I'll not do it 200 times here. So space charge compensation, this was Phil Bryant who did this. You see that we had a huge working line going from, if you look at the straight part, here. Oh, this is a, well, I will not use that, no. You see the huge working line from minus 42 millimeters, we call it, plus 45. You needed this huge amount of Q spread for stability, and you needed the large amount of delta P over P to store the beam. So you ended up having a Q range of something like 0.07. And if you look at a tune diagram with resonances, to fit that into the tune diagram is close to impossible. And this was one of our initial lines, and you see that it crossed fifth order resonances at the bottom and almost went up to third order resonances at the top. So the stack was actually made between the third order resonance and the fifth order resonance, but during acceleration of the beam we crossed fifth order resonances. This was a breakthrough, the first Schottky scans. These scans were taken on the top at 10 amps, the middle one 15 amps, and the lower one now just over 19 amps. And Schottky scans originated, this was Vandermeer who proposed this, I think in 1968, that the discrete nature of the particles would allow you to look at these scans, and this was a longitudinal scan, and what we get from this is the longitudinal density on the vertical axis, and more or less the energy or the momentum on the horizontal axis. So we now had Schottky scans. One of the big disadvantages of the ISR was the fact that we injected on the inside, and the injection inflector was on a movable girder, and you put this in during injection, and at the end of the stacking you pulled it out, which meant that you ended up with this beam very much off-center, not in the center of the aperture, and this caused huge background problems in the beginning. And now that we had the Schottky and space charge compensation, we were able to increase the dipole field, modify the space charge compensation, and move the beam into the center of the vacuum chamber. And we did this here, and this is a couple of examples. We did it typically by 10 millimeters, and if you see the table on the bottom, you see the two runs, the loss rate dIdt in parts per million per minute. Before displacement was 60 ppm on the ring 1 and 10 on ring 2, and after the displacement 0.8 and 0.8. And this transformed physics data taking, just this simple thing, because we now had a little bit of diagnostics which we could use. Phase displacement, I don't think anybody else has ever done phase displacement. We knew that we could go to 31.4 GeV, but the PS could only inject at 26. So we could have a big coasting beam with 3% momentum spread. We wanted to increase that with 40 amperes up to higher energy, 31.4. We had a RF system which only had 16 kilovolts, so it looked like an impossible task. But there was some work done previously which showed that if you pass empty RF buckets through a stack, you can increase the energy. And I'm trying to show this here. The green part's the stack, and the red thing going from top to bottom is the bucket. And that's how it's basically how you had to do this 200 times to go from 26 to 31. So we undertook this, not knowing what all the problems would be. And I see Keith there. I remember having dinner with him one night and talking about all the problems. But there was space charge problems, there was RF noise problems, there was every sort of problem you could think of. In phase space for the accelerator physicists, this is what it looks like rather than a simple diagram. So you now know that you can change the energy of a beam by moving empty buckets through it. But if you only change a small part of the energy of the beam, and this is what we did here, the 4 spikes you see, we moved all but the top end of the stack down in momentum. Then we moved another little bit down in momentum, and these made beautiful little markers on the Schottky scan. In the top right, you see a longitudinal Schottky scan where you have the markers for the top and bottom of the stack, but in the middle of it, you see these dips, and these are clear markers on the longitudinal Schottky, and that tells you where the marker is. You know where the delta P over P is, and you see the same transverse Schottky, and therefore you get the tune value. So now we have, by putting those markers on, we have the working line, okay? And you see from my poor handwriting that everything was done by hand in those days. And this is QH and QV against delta P over P, and you see the working line. And the beauty of this was we set up this working line at the beginning of a physics fill, and it lasted all the way through the physics fill, so we could see what was happening as we lost current and the beam became bigger and so on. Now this is, I'm only 9 minutes, good. This is working line close to an integer resonance, due to the integer resonance. I've said before we were always looking for somewhere to place this 0.07 Q range. And it's fairly clear when you look at the resonance diagram that if you want to do this, the best place to work is close to the integer resonance. There's a maximum amount of space around the integer, and next it's the half integer, and that's why we operated where we did in the first place. We decided to have a new line, I think it was called ELSA, and we put this line, the top of the stack was at 8.955. Most people thought this was crazy, just 0.045 away from the integer. Initial operation at these tunes was very problematic. We had all sorts of problems with stability, orbit stability, transverse stability. Finally, with time, all of the problems were solved, but there was one effect which was unknown at the time, which caused a massive increase in the beam emittance at the top of the stack. And this really ruined physics and so on. The sodium curtain showed transverse cross-sections which looked like lacrosse sticks. Some of us proposed a mechanism for this, and I did an experiment, and this is the experiment. On the left-hand side we stacked a beam at the top, 8 amperes, and in the other ring, at injection, we put 80 milliamps, one small injected pulse. We left the small injected pulse in the other ring and looked at what was happening, and after 6 minutes, you have afterwards, there's only 3 amperes left, and the whole top, if you look at this scan, the whole top of the stack is completely eroded. And that's caused by the beam-beam effect coming from 80 milliamps in the other ring. And this we called overlap knockout. Not many people have heard of it, but it was a very, very significant effect in the ISR. And this is it here. Basically, if you look at the bottom, I'll try this thing again. If you look at the bottom here, what happens is if there's an overlap between the bunched beam at injection, its frequency spectrum, and the transverse frequency spectrum of the other beam, then you get an RF knockout effect. RF knockout means if you hit a resonator at its resonant frequency, it just grows. And this is exactly what was happening. Now, this shows you in a bit more detail that if you work close to the integer, you have more and more problems with the lower harmonics of the bunch frequency. And this was very important for us. We looked at a large number of reasons and resonance conditions, but the most important was the two-beam dipolar effect, and this was caused by the delta P over P difference between the injection orbit, in our case, and the storage orbit. But this can also be important for other machines with particles which have different species. With different species, different revolution frequencies, and you can have this overlap resonance condition. Accelerators like LHC, if it's going to work with ions and protons, or like RIC, the only way you can do this is, if possible, to lock the RF frequencies of both rings. So we looked at cures for this, and we found two very simple cures. One of the first things we did was we reduced the amplitude of the higher harmonics of the bunch spectrum by simply lengthening the bunch of the injected beam, by reducing the RF voltage, making the bunch longer. The other thing we did was we looked at the separation in the injection regions, and then arranged that the vector sum of each beam-beam kick was minimized over one turn, and we called those good bumps. And we tested good bumps against bad bumps, and there was a factor of 1,000 different between the two. So we used these operationally, and that's one of the reasons why that line finally started to work. This is another interesting experiment, which has nothing to do with colliding physics or anything, but it was very interesting for several of us to look at. We had deuterons and protons possibilities in one of the rings. So we injected 3.3 amperes of deuterons, and then we injected in the same ring, going in the same direction, protons. And we accelerated the protons so that in real space, the top diagram, you see on the dense part here, this is protons and deuterons, and the rest, the long bit, is the deuterons. But if you look on phase space below on the Schottky scans, you see a complete separation between deuterons and protons. The amazing thing for me was these millions of particles are all going together all around, and we were able to separate the protons out by doing phase displacement of the protons. So we phase displaced these protons, doing it again, here. We decelerated them on their own down to an aperture limitation on the inside and got rid of them and only had deuterons left, which was a neat experiment. This is the vacuum evolution. The continuous work went on in the vacuum. We ended up with a vacuum pressure of something like 3 × 10⁻12 average throughout the ring. But this was many, many years of work and various things like bake out at 300 degrees centigrade, glow discharge, and lots of other things. This is the luminosity evolution with time, and you see the design where it is. This is the iconic experiment which Carlo talked about. And this experiment used the measured luminosity in the ISR to see if there was cooling. And Kurt Hubner was the person who proposed this and coordinated it. And you see it's a very small effect, but it's a very clear indication that stochastic cooling works. And this was the first indication. And the one below was shown by Carlo. This was not very long later, not very much time later, when you see the effect of cooling, longitudinal cooling, in the initial cooling experiment, which is much more impressive than the ISR, but the ISR showed that it worked. So, finished ahead of time, you'll be happy to hear, Freddie. This is what I think is the legacy of the ISR. Stacking of protons, nobody does it anymore. That's the only cue. Ultra-high vacuum, there's a lot of work went on there, clearing electrodes. We saw the electron cloud, and that's relevant for the LHC. We built very high-precision power supplies, again, very relevant for the LHC. Low-impedance machines, this was Wolfgang Schnell's real baby. He wanted the lowest impedance of machine you could get, and that was also passed on to PP bar S, plus LEP, plus the LHC. We had this overlap knockout. There may be some effect for LHC in the future, but not many accelerators work that way. Nobody ever has used space charge compensation because it was such a large momentum spread. Collimation was one of the things which was very, very well understood in ISR. Luminosity scans, what they call Van der Meer scans now, they were done for the first time in ISR and now are done in LHC. I'm not sure whether they were done in the PP bar S. Phase displacement acceleration, no one else would ever dare do anything as stupid as that. Schottky scans, again, SPP bar S, Schottky stochastic cooling, again, SPP bar, very, very impressive, and possibly sometime in the future at LHC. Low beta insertions, proton, anti-proton collisions, nothing about stacking and phase displacement. Thank you very much.
Thank you very much, Steve. As usual, very efficient, very time respecter. Thank you very much. Okay, maybe we have the time for one short burning question, if you have one. Okay, you have a microphone in front of you.
Hello, thanks. I was wondering if you ever encountered some sort of technical limitation that surprised you while you were assembling ISR, and how did you handle it?
Technical innovation. Well, certainly stochastic cooling surprised me enormously, and Schottky scans. And it was such a major breakthrough. It was impressive because we had no diagnostics until we got Schottky. And then once we had Schottky, mostly Wolfgang Schnell was the person. He realized that if you could see it, you could cool it. And that was the beginning of stochastic cooling. So that's, for me, the most important thing. There are many other things, but not as important as stochastic cooling.
Okay, I think we have to move on. Thank you very much.